Okay, and welcome to this lesson where we are going to convert binary into denary and denary back into binary. So in class we've been doing some of this already. We're going to reteach the binary to denary and then the denary to binary, and we're going to practice both of those as it's really important that we have a good understanding of them. So first up, we're going to start with a 4-bit piece of binary, also known as a nibble. Now with this we're going to have value channels based on the number of bits of binary we are converting. So for example, if I only had one bit, either a 0 or a 1, I would start with 1. But for every additional channel of bits that we have in our binary, we're going to double the next value. So 1 is doubled to 2, 2 is doubled to 4, and 4 is doubled to 8. And it is done in reverse. From left to right, not left to right, sorry, right to left, as opposed to left to right, which is the normal way we would write. So what we've got to do, once we've recognised we've got 4 bits of binary and we've got our values in, we are then going to place our binary underneath. And in this stage, what we have to do is simply keep any of the numbers that have 1 underneath. So 1 we're going to keep, 2 we don't need, 4 we don't need, and 8 we're also going to keep as a value of 1. So we have 8 and 1. So the next stage is to simply add them together. And at this level, with 4 bits of binary, this should be fairly straightforward. Now, if we had 64 channels with some very, very, very large numbers in there, we would definitely need a calculator and more time. Thankfully, we don't need to do 64 bits of binary. We're only doing 4 at the moment. So the maths is nice and easy, 8 plus 1, and that leaves us with a binary which is 1001 is a denary value of 9. Okay, so nice and straightforward. So let's go through that process again, but this time we're going to use 5-bit. So as I said before, we start with 1 for one value channel, and every time we had another bit of binary, we simply double the previous value. So we've gone from 1 to 2, 4, 8, and now we've got a 5th channel, so we've gone from 8 to 16. So let's have a look at this. So we're going to place our binary values underneath as before, and the next stage is to simply keep the ones with a value of 1 and remove the ones that have a value of 0 underneath. So we're going to keep the 16, the 8 and the 2. And then as before, all we need to do now is add them together. And that gives us a grand total of 26. So a piece of binary that has 1, 1, 0, 1, 0 is 26 in denary. So let's have a look now at a more traditional length piece that we use in computer science at Key Stage 3. And we have an 8-bit piece of binary. So I've gone ahead here and I've doubled those values, and as you can see, going to 8-bit really does start to bring some bigger numbers into play. And if we was to do this again, we'd keep doubling up and going on, and modern computers that are 64-bit would continue to go with some very, very large numbers. So as before, we simply add in the binary underneath, and all we need to do is keep those values that have 1 underneath and disregard the rest. So we're going to add 64, 16, 8, 4 and 2 together, and that leaves us with a value of 94. So what I'd like you to go and do now is to use the same process to answer the questions on section 1 on the sheet. So pause the video if you're watching and go and get this resource from Satchel or wherever your school or education provider is sharing this to you from, and you're going to complete section 1. There are 6 questions and you can resume the video once you have completed them. Okay, so let's continue with this now. So you might be asking a question, but what about denary to binary? Well, we're going to use exactly the same numbers that we used in the previous example, and that way we can check if they're right. We can see if it is working or not, because we'll be able to check with the binary we just used. So we're going to start with a denary number of 9, and all we have to do is divide that number by 2. When we divide it by 2, we then have to ask the simple question, does this answer have a decimal or not? If the answer is yes, we give it a 1. If the answer is no, we simply give it a 0. So 9 divided by 2 is 4.5. Does it have a decimal number? Yes. So we put a value of 1. Next up, we're then going to carry forward only the whole number. We do not carry forward the decimal. So we take the 4 and we leave the 4.5 behind in the void. We do not need the 0.5. So we're going to take the 4, divide it by 2. That leaves us with 2. And is that a decimal? If the answer is yes, it would be a 1. But the answer is no. So we place a 0. Next up, we carry forward the whole number. So we carry forward the 2. We divide it by 2. That gives us a 1. So is 1 a decimal number? The answer is no. So that is a 0. We then carry forward the whole number, divide it by 2. That leaves us with 0.5. Is that a decimal? Yes. So we place a 1 next to the end of that sum. So let's look at that number, 1001. So that was the number we started with in binary, which we converted to denary, that gave us the 9 to begin. So we know it's correct. Now, once we get to the point of carrying forward a 0, so we disregard the 0.5, we stop. So once we get to a value of 0, we can no longer do any more sums, so we stop there. So 1001 is a 4-bit piece of binary, also known as a nibble, and therefore we know that is correct because that's what we started with before. Okay, let's do another one. So let's start with 26, which was the second piece we did. Now I've gone ahead here and placed out 5 divide 2s because I already know that this number is going to be 5-bit because that's what we started with before. We might not always know that, so sometimes we just have to follow the number, and we will look at a special case of that very shortly. So we start with 26, we divide it by 2. It leaves us with 13. Is this a decimal? If it's a yes, it's a 1. If it's a no, it is a 0. There is no decimal, it is 0. We carry the whole number only forward and we divide by 2 again. That leaves us with 6.5. Is there a decimal? Yes. So we carry forward only the whole number, no decimal. That leaves us with 6. Divide by 2 is 3. It's a whole number, we place a 0. We carry the 3 forward, the whole number only. Divide by 2, 1.5. Is there a decimal? Yes, it's a 1. Then we have carry forward, the whole number only. So the 1 gets divided by 2, that leaves us with 0.5. That is a decimal, we place a 1. Then we carry forward the 0, and because we can't go any further with a 0, we stop. That leaves us with a 5-bit piece of binary. And I want you to take a special note here that we start with the highest value on the right hand side, okay, and then we work down the list, writing from right to left in this direction. So the top value is in the very far channel, which would be labeled 1 if we were doing this the other way around, and then we add in the rest of the numbers in reverse. It's a very, very important stage. Otherwise, you could end up with the wrong binary number. So the direction of this is absolutely critical. So the highest number is on the far right, and as we work down the list of binary, we put them in from right to left. In other words, from our Western perspective, we are writing backwards. So let's do one more number now. We're going to take 94, and as we said before, we know roughly how many channels this is, but you will notice that I only have 7. rather than 8. And this was an 8-bit piece of binary, and I'll explain that very shortly. So we start with 94 divided by 2, 47. It's a whole number. There's no decimal, so it's a 0. 47 divided by 2 leaves us with 23.5. That decimal leaves us with 1 because there's the decimal. We carry forward the whole number only. And I'm just going to work through these sums. So we've got all of these now, and you can see the maths. And then we get to 0. And at 0, we've still got a blank channel. So remember that this is an 8-bit piece of binary we used before, but actually it could work as a 7-bit piece of binary. There's an additional channel which is not accounted for. So what happens is all the remaining blanks are all 0. So when we write this in reverse, so we start at the top where it says 94, we start with this 0 and we write it out. As we ended with 1, which is here, you see this 0. We simply add in all the zeros that we wanted. So if we had an 8-bit piece of binary that was the number 9, we would simply add in onto this number here, where we've got the 4-bit, 4 zeros at the end, and that would be an 8-bit number 9 if we was to put those in. So just to clarify, if we run out of bits and it's asking for 8-bit, but we only have 7 value channels, at the very end we add the remaining missing zeros to make up that bit. So if I wanted to turn this into 9-bit, I would simply add another 0 at the end. If I wanted to change it to 10-bit, I would add in 2 zeros at this end, and so on. So let's look at worksheet section 2. So here are some tips for that. So first up, the number of bits equals the number of digits. So I've done a little list here to sort of show you how that works. Okay. We then have the steps involved to convert denary into binary, and I have an example of that here using one that only has 7 bits. From working out what is required an 8-bit answer, so we add the extra 0 on. So can you please complete and hand the worksheet to the teacher in class? So you need to hand this working out sheet to me in lesson, or your teacher in lesson if I don't teach you. And then I want you to add in your final answer to the Microsoft Forms. That link is on Satchel if I teach you. And you're going to add those answers in, and that way you can check if they are correct or not. I will mark the home learning as being complete when both parts are handed to me. So go ahead. If you have any problems, please contact your teacher on Satchel or whatever platform your school uses. In this school where I'm from, we use Satchel. So please contact me there if you have any problems. I will not respond to you on YouTube at all. So please do not contact me on here. Thank you and good luck.